Okay, I did some remodeling for the last problem to make it look nicer, right? And I fixed the mistake. But let's look at number 10. We'll say this is the series n equal 3 to infinity of 1 over n to the 0.9999. We would say p is 0.9999, which is less than 1. And if it's less than 1, therefore diverge. You're supposed to say diverge by p series. But we are going to reserve the letter p for the p series, so there it is. Anytime you say p equal, I assume you're talking about p series. And if you're not sure, write by p series. On the next problem, we want to take a look at this, and this is the series of 1 over, this is arithmetic. So a sub n is a sub 1 plus n minus 1 times t. The very first term on the list is a 5, n minus 1. The common difference, you're adding a 2 every time. That's 2n plus 3. That's pretty much it, right? This is continuous, positive, and decreasing. Now, we know this behaves like n to the 1, right? And we know that diverge, but it's not n, so it's not that clear. We have to show it. We would take the integral from 1 to infinity of 1 over 2x plus 3 dx, and that would be 1/2 natural log of 2x plus 3 evaluated from 1 to t, taking the limit as t approaches infinity. That would be the limit as t approaches infinity of 1/2 natural log of 2t plus 3 minus natural log of 5. That will approach infinity, and therefore it'll diverge by the integral test. Alright, and that's really how we play with those. How about this? Well, this is not arithmetic nor geometric. This is the series n equal to infinity. This is a sub 1, this is a sub 2, this is a sub 3. So do you notice it seems the top is always 1. A sub 2, 2 times radical 2. A sub 3, 3 times radical 3. A sub 4, 4 times radical 4. A sub n, n times radical n. And wouldn't you say this is the series n equal 1 to infinity of 1 over n to the 3/2? Wouldn't you say p equal 3/2 bigger than 1? Therefore, you could say converge. You're supposed to say by p series, but if you use the letter p, we're fine. And that's all there is to it. That's the beauty of the p series. It'll save you a lot of work. The next problem on the list is number 16. Well, we know that's continuous, okay? Because it only, that's a square root. It can never equal, that's a square root of n cubed, right? That's positive. Plus 1, that's always positive. Again, you only say continuous, it better be continuous. Well, they're not going to trick you. Positive, that's fine. Decreasing, not so fast. If you want to say decreasing, you have to show that. And how do you do that? You go on the side, you say, all right, well, let's see. What is f prime? F prime is derivative of the top. That's 1 over twice the square root of x times the bottom minus the top times derivative of the bottom all over the bottom squared. And if you clear the fractions by getting a common denominator for the top and the bottom combined, multiplying by 2 radical x, this is 1 plus square root of x cubed minus the radical cancel out. You'll get 2x, and the 2's cancel out. Actually, it has the 2 already. So if you multiply this just by radical x, that'll do it. Right? That would be x times x to the 1/2. And the denominator will be twice radical x into 1 plus x to the 3/2 squared. And if I look at this, that's actually twice the square root of x into 1 plus x to the 3/2 squared. And that will be 1 minus, okay. There's a 3 there. So that's 3 of those plus 1 of those, that would be 2 of those. And pretty much you're glancing at this and figuring out, well, how am I going to do my testing and where am I going to look? Well, let's see. 0 is a point, and that's it. This can never equal 0, like we said. This is a square root equaling negative. That's not going to happen. I has no room in this class. So if I pick a point to the right, let's say 1, and I put it in there, that's positive, positive. 1 minus 2 is negative. So if f prime is negative, f is decreasing. Now I could claim that, and that's fine. I still need to integrate that. Okay, so we still have to integrate this. This is the square root of x over 1 plus x to the 3 halves, integrated from 1 to infinity, in this case dx. If I let u equal 1 plus x to the 3 halves, du will be 3 halves x to the 1 half dx. So this will be my du. So that is 2/3 the integral of 1 over u du. That's going to be 2/3 natural log of u, right? And that's going to end up being 2/3 natural log of 1 plus square root of x cubed minus, let's go in order. Evaluate from 1 to t, taken the limit st approaches infinity. That's the limit st approaches infinity of natural log of 1 plus the square root of t cubed minus natural log of 2. That's going to approach infinity, therefore diverge by integral test. Now we're going to talk about a very important idea, remainder or error. That's going to come up in almost every section of 11.3, 11.4, 11.5. So, and each of those has its own formula. We don't want to memorize those. We want to understand them. So, a series runs from 1 to infinity. Well, since those are going to be decreasing for the most part, not that you have to really worry about that. Let's say, actually, let's say I took those four. Let's say I said this series is a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. That's it. And I stop right there. So this series, and I'll do an example and show you how that works and why that works. I just want to add the first 4 terms, and I'm going to say that's what this infinite series equals. Do you see what I left out? Wouldn't this be the remainder? Or we call it the error in the approximation. We left out those infinite terms. So, we could say this is a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus the series n equal 5 to infinity of a sub n. And we could refer to this sum as the actual error. And now I'm going to show you something about continuous versus discrete. Suppose I'm looking at this graphically. Suppose these are the domain, this is the domain, and this is the a sub I. So if I say a sub 1, let's say a sub 1 is that right there. A sub 2, a sub 3, a sub 4, and I stop right there. Right? There's still a sub 5, so I'm talking about this. Now, if I want to talk about a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, well, that's the first 4 terms. If I want to talk about the integral from 1 to 4, the integral would be the continuous part. So assume the function is something, not necessarily 1 over x, something like that. Well, if I integrate, instead of finding the specific values, which is discrete, if I integrate all the way to 4, here I am, right? Now, the difference is, if I integrate from 1 to 4, let's say f of n dn, well, versus a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. If I want to pick up where I left off, I start with a sub 5 plus a sub 6. If I want to pick up where I left off, I start with 4 and I pick up to infinity f of n dn. So, if I really wanted to pick up, I have to pick up at a sub 5, then a sub 6, then a sub 7, as far as discrete. But if I want to integrate, there's that extra piece added right there. So, I could say, and I'm going to make this really simple so there's no confusion. I'm going to say, if I take the series, so the error here is the series n equal 5 to infinity of a sub n. And here from 4, I'm going to say the series n equal 5 to infinity of a sub n is less than, and I'm going to even make it equal because I don't want to prove it, to the integral from 4 to infinity of f of n dn, if you convert everything accordingly. And that's how things are going to play. Now, inequality you're not very comfortable with. You're going to get very comfortable with that in the next section. I'm going to rearrange things and look at an example. I want to look at number 36. In the book it says we have this infinite sum. We have a series n equal 1 to infinity of 1 over n. It says estimate the error in using. They're not saying find in you. Oh, here I've seen. They say find. I'm sorry. So take a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus all the way 10 to the 4th. That's where you're going to stop. What's the error? The parts you left out is the series n equal 11 to infinity of 1 over n to the 4th. If this is geometric, I can find it and I'm done. If it's not geometric, I'm going to say this is less than or equal to the integral from 10 to infinity of 1 over x to the 4th dx. I'm going to integrate that. And I'm going to say that is and I'm going to work sideways instead of moving downwards. That's going to equal the limit as t approaches infinity. That's going to be x to the negative 3 over negative 3. So 1 over negative 3 x to the 3rd evaluated from 10 to t. You know what? Let me not break my rule because that's how I wanted to work on the test. Downwards. And that's going to be the limit as t approaches infinity of 1 over negative 3 t cubed plus 1 over 3 times 10 cubed. That would be 0. And the error is less than or equal to 1 over 3000. So far so good. That's 0.0003. Now if you added those accurately, this turns out to be, that is this sum. This green sum turns out to equal 1.083237. So this is telling me this is accurate to 3 decimal places. You can't trust these numbers. And what if you want more accuracy? What if you want to test 1, 2, 3, 4? What if you want to have it accurate to this number? So here I want the error to be less than 0.00001. The error is really the integral from n to infinity of dx over x to the 4th, but I already worked that out. That is really the limit as t approaches infinity of negative 1 over 3x cubed evaluated from n to t, right? And here I am gonna take negative 1 over 3t cubed plus 1 over 3n cubed. The limit as t approaches infinity, this would be 0. I want that to be less than 0.0000123 Now, you are allowed to treat this like an equation and find the LCD and clear the fractions because n is always positive. and n would be bigger than the cube root of 1 divided by 3 times 0. And that would be 32.18. So if I set it equal to 33, I could always be over accurate, not under accurate. That would be it. And there's the homework.